Good morning, everyone. Today I will be presenting on the foundation knowledge required for wireless communication. This comprehensive overview covers essential concepts that underpin all wireless communication systems from basic radios we grew up with to the sophisticated 5G networks powering our modern connected world. Let's move on to the next slide. Agenda. Let me outline what we'll cover today. We'll begin with a brief introduction to set the context, then dive into fundamentals of wireless communication, examining signals, transmissions, and the critical concept of decibels. We'll then explore advanced signal concepts and principles before covering wireless communication basics, including antennas and data communication principles. We'll also discuss network protocols, security mechanisms, wireless LANs, and conclude with advanced networking technologies. This journey will give you a complete picture of what makes wireless communication possible. We'll move on to the next slide. Overview of wireless communication. Wireless communication has fundamentally transformed how we connect and share information in the modern world. Instead of being tethered by physical cables, wireless technologies allow us unpredictable mobility and flexibility. Consider how we evolved from simple radio broadcast and that could only transmit in one direction to today's sophisticated 5G networks that supports everything from high definition video streaming to autonomous vehicle communication. What What's fascinating is that despite the incredible diversity of wireless applications we see today, they all rely on a common set of fundamental principles and concepts. Understanding these building blocks is crucial for everyone looking to work with it, design, or simply appreciate wireless technologies. Today's presentation will systematically explore these foundations deeply. Let's move on to next slide. The purpose and scope of this research paper. This presentation aims to provide a comprehensive understanding of foundational knowledge required for a wireless communication. We'll cover signal transmission fundamentals, networking protocols, multiplexing techniques, and security considerations. By the end of this presentation, you should have solid grasp of the key concepts that underpin wireless communication systems. Signal fundamentals. Let's start with basic of signal fundamentals. We'll discuss frequency, wavelength, amplitude, and phase frequency measured in hertz. Represent the number of wave cycles per second. Different technologies operate in different frequency bands, such as wavelength is inversely proportional to frequency. Following equation is wavelength measuring equation. C is the speed of light and F is the frequency. This relationship means that high frequency signals have short wavelengths, while low frequency signals have long wavelengths. This fundamentally affects how signals interact with the environment. Lower frequencies can penetrate buildings better, while higher frequencies can carry more data. Amplitude refers to the maximum displacement or strength of the signal. Corresponding to its power or intensity, higher amplitude signals can travel farther but require more energy to generate. Phase describes the position within the single cycle of waveform, measured as an angle in degrees or radius. Phase relationship between signals are crucial for many modulation techniques and understanding interference patterns. Move on to next slide. Transmission characteristics. When we talk about transmission challenges, we need to consider three major phenomena: path loss, multipath progression, and fading. When it comes to path loss is the reduction in power density as a signal propagates through a space. Following the inverse square law, signal power decreases with the square of the distance. This means that doubling the distance reduces the signal power to 1/4 of its original value. Path loss is also affected by obstacles and atmospheric conditions. Multipath propagation occurs when signals reach the receivers through multiple paths due to reflection, diffraction, and scattering. Depending on the phase relationships, this can cause either constructive interference strengthening the signal or destructive interference weakening it. When it comes to fading, fading refers to a variation in signal strength over time and frequency caused by multipath propagation and in movement of transmitter receiver objects in the environment. Fading can be classified as fast, as slow, and as flat of frequency selective, each requiring different mitigation techniques. Decibels in wireless communication. Now let's discuss the concept of decibels, which is fundamental to wireless communication. The decibel is a logarithmic unit used to express the ratio between two values. The logarithmic nature is particularly useful for representing the wide range of power levels in wireless system. For power ratios, we calculate decibels as PdB equal 10 multiplied by log 10 P2 divided by P1. For voltage ratios, it's VdB equal 20 multiplied by log 10 V2 divided by V1. Common decibel measurements in wireless system includes dBm, which represent power relative to milliwatt, and dBi, which indicates antenna gain relative to isotropic radiator. dBd, antenna gain relative to dipole antenna. Signal transmission and bandwidth. Bandwidth in wireless communication refers to the range of frequencies a signal occupies, directly affects data carrying capacity of wireless channel, and its relationship with data rate is governed by fundamental information theory principle. We'll move on to next slide. Shannon's capacity formula. Let's explore the relationship between bandwidth capacity through Shannon's groundbreaking channel capacity formula. C equal B into log 2 1 plus SNR, where C is the channel capacity bits per second and B is the bandwidth in hertz and SNR is the signal to noise ratio. This elegant formula developed by Claude Shannon in 1948 establishes the theoretical maximum data rate achievable over communication channel. It reveals a fundamental tradition of we can increase capacity either by expanding bandwidth or improving the signal to noise ratio when spectrum is limited. As it often in commercial wireless systems, engineers focus on improving SNR through better modulation techniques, error correction, and noise reduction. For example, increasing SNR from 10 to 100 only increases capacity by a factor of about 3.3, while increasing bandwidth from 10 MHz to 100 MHz increases capacity by a factor of 10. This mathematical relationship drives many design decisions in wireless systems. Let's move on to next slide. This slide will explain about the error control mechanisms in wireless systems. For reliable communication over inherently error-prone wireless channels, we employ various error control techniques. First one is error detection. Methods like checksums, parity bits, or cyclic redundancy checks identify errors but can't correct them. CRC is particularly powerful as it is as it can detect all single bit errors, all double bit errors, and many burst errors. Second one, forward error correction, FEC, adds redundant data to message that allows receiver to detect and correct error without requesting transmissions. Techniques like convolutional codes, Reed-Solomon codes, and turbo codes can recover from various error patterns at the cost of transmission overhead. Third one, automatic repeat request. This represent is a feedback-based mechanism where receiver requests retransmission of data packets detected as erroneous. Three common variants are stop and wait ARQ, go back in ARQ, and selective repeat ARQ, each making different trade-offs between efficiency and complexity. Modern wireless systems typically employ hybrid ARQ schemes that combines FEC and ARQ, which means forward error correction and automatic repeat request, adaptively balancing reliability and the throughput based on the channel conditions. In this slide, MAC addresses and flow control will be explained. When it comes to MAC address are unique identifiers for network interfaces, crucial in wireless networks for device identification and access management. When it comes to flow control mechanisms, regulate data transmission to prevent buffer overflow, but are complicated by variable nature of wireless channels and asymmetry between uplink and downlink capabilities. Next slide. In these slides, we'll do a comparison between transmission control protocol and user datagram protocol. Comparing TCP and UDP reveals fundamental differences in how these transport protocols handle data. Transmission control protocol is connection oriented, establishing a session before data transfer. It ensures reliability through acknowledgements and retransmissions, maintains packet ordering, and implements sophisticated flow and congestion control mechanisms. This 20 to 60 byte header overhead is worthwhile for applications like web browsing and file transfers that require absolute reliability. When it comes to user datagram protocol, in contrast, is connectionless with no guarantees for delivery ordering. With just an 8-byte header, it's significantly more lightweight but places reliability responsibility on application layer. This makes UDP is ideal for real-time applications like video streaming and online gaming, where timeliness is more important than perfect reliability. In wireless environments, transmission control protocol reliability mechanisms can sometimes interact poorly with the inherent variability of wireless channels. For instance, transmission control protocol might interpret losses due to wireless errors as congestions and unnecessarily reduce transmission rates. Modified versions of TCP developed for wireless networks specifically to address these wireless challenges. We'll move on to next slide. In this slide, data encapsulation process in TCP/IP model will be discussed. Data encapsulation is process of layering protocol information as data moves through the networking stack. At the application layer, data is generated according to protocols like HTTP or FTP. The transport layer segments this data and adds TCP or UDP headers, and the internet layer adds IP headers to the create packets or datagrams. The link layer adds MAC address headers and trailers to form frames. Finally, the physical layer converts these frames to bits and transmits them as signals. In wireless networks, this process must accommodate the unique characteristic of the wireless medium, particularly at the physical and link layers where signal modulation, error correction, and media access control are tailored to wireless environment. We'll move on to next slide. In this slide, we learn about antennas. Antennas are the critical interfaces between guided electromagnetic waves in circuit and unguided waves in free space. Their performance is characterized by several key parameters. First one, the radiation pattern shows the spatial distribution of radiated energy. This three-dimensional pattern reveals where an antenna concentrates its energy and where it has nulls, or areas of minimal radiation. Understanding this pattern is crucial for proper antenna placement and orientation. Directivity quantifies how focused an antenna's radiation is in a particular direction compared to an isotropic radiator, which radiates equally in all directions. High directivity means more concentrated energy in specific directions, which translates to longer range in those directions but reduced coverage in others. Gain. Gain is similar to directivity but accounts for antenna's efficiency. Not all input power gets radiated due to recitative losses. Gain is typically expressed in dBi, decibels in relative to an isotropic radiator. For example, simple dipole antenna has approximately 2.15 dBi gain, while directional Yagi antenna might have 10 to 15 dBi gain. Next one, beam width. Beam width refers to the angular width of the main lobe in the radiation pattern, typically measured at half power 3 dB points. Narrower beam width indicates more focused energy and higher gain, but requires more precise aiming. Polarization. Polarization is the orientation of electrical field vector of the radiated wave. Vertical, horizontal, circular, and elliptical for optimal reception. Transmitting and receiving antennas should have matching polarization. Mismatched polarization can result in significant signal loss. There are different antenna types serve various applications based on their characteristics. The first one is omnidirectional antennas. Like dipoles and monopoles radiates equally in all horizontal directions, making them ideal for mobile applications where orientation is constantly changing. Your typical Wi-Fi routers uses omnidirectional antennas to provide 360 coverage. Directional antennas such as Yagi. Panel and parabolic dish antennas focus energy in specific directions. This provides higher gain, longer range in the target direction, making them suitable for point-to-point links or serving specific coverage areas. Multiple input, multiple output antennas. And these antennas use multiple elements at both transmitter and receiver to exploit multipath propagation. Rather than fighting multipath as a problem, MIMO leverage its create multiple spatial channels, dramatically increasing capacity without additional bandwidth. This technology is fundamental to modern Wi-Fi systems. The selection of appropriate antennas significantly impacts system performance, determining coverage, capacity, and the reliability of the wireless networks. Let's move on to next slide. Analog versus digital signals. Wireless systems handle both analog and digital signals. Analog signals are continuous and vary smoothly over time, directly representing physical quantities like sound waves. Traditional AM and FM radio broadcast uses analog signals where the amplitude or frequency directly corresponds to the audio being transmitted. Digital signals are discrete, representing information as sequence of binary digits. Modern wireless systems predominantly uses digital signals because they offer remarkable advantages. First one, immunity to noise and interference. Second one is error detection and correction. Mathematical technique can identify and often fix the transmission errors significantly. Let's move on to next slide. In this slide, we will discuss multiplexing techniques. Multiplexing techniques allows multiple signals to share the same communication channel, maximizing spectral efficiency. First one, frequency division multiplexing divides the available bandwidth into non-overlapping frequency bands. Example includes FM radio stations broadcasting on different frequencies and cable TV channels. This technique is straightforward but may be inefficient if some channels are idle. Second one, time division multiplexing allocates entire bandwidth to users for designated time slots. GSM cellular systems use TDM, allowing multiple calls to share the same frequency band. This approach requires precise synchronization between transmitters and receivers. CDMA, code division multiple access, allows multiple users to transmit simultaneously across entire bandwidth by assigning unique spreading codes. Each transmitter multiplies its signal by high rate code sequence, spreading its energy across with wide bandwidth. Receivers use the same code to extract the intended signal. This technique is resistant to interference and eavesdropping but computationally intensive. OFDM, orthogonal frequency division multiplexing. OFDM divides the channel into multiple orthogonal subcarriers, each modulated with conventional scheme by converting a high-speed data stream into multiple parallel lower-speed streams. OFDM efficiently combats frequency selective fading and narrow band interference. This technology forms the foundation of Wi-Fi, 4G, 5G, and digital television broadcasting. And there are two other multiplexing techniques as well. Space division multiplexing, we called SDMA, and we will discuss about advanced division multiplexing. We'll move on to next slide. In this slide, we discuss about multiple access technologies. In wireless networks, multiple devices share the same medium requiring efficient access control. Random access protocols like Aloha, slotted Aloha, CSMA, CSMA/CD, and CSMA/CA help manage collisions. Performance is influenced by propagation delay. In this slide, we discuss about the IEEE 802 standards. The IEEE 802 standards define a specification for various network technologies. IEEE 802.3 encompasses the Ethernet standards for wired LANs, from original 10 Mbps to today's 400 gigabits per second implementations. IEEE 802.11 defines the wireless LANs, which means Wi-Fi standards. 802.11a operating in 5 GHz band with up to 54 Mbps using OFDM. 802.11b using 2.4 GHz bands with up to 11 Mbps using DSSS. 802.11g combining the best of both with 2.4 GHz operation and up to 54 Mbps using OFDM. 802.11n introducing MIMO technology for up to 600 Mbps across 2.4 to 5 GHz bands. 802.11 AC enhancing performance with wider channels, higher modulations, and MU-MIMO for up to 6.9 gigabits per second. 802.11ax is Wi-Fi 6 optimizing efficiency in dense environments with OFDMA and improved MIMO. IEEE 802.15 covers wireless personal area network standards, including Bluetooth for short-range device connectivity and Zigbee for lower power applications like IoT sensors. IEEE 802.16 defines WiMAX standards wireless metropolitan area networks provisioning broadband wireless access over long-range distance. These standards define both physical layer specification for signal transmissions and media access control layer protocols for the channel access, ensuring interoperability between devices from different manufacturers. We'll move on to next slide. On this slide, we discuss about the infrastructure-based wireless networks. Infrastructure-based wireless networks use central access points or base stations to coordinate communications. They include basic service sets, extended service sets, and distribution systems. These networks offer centralized management, easier security, and extended coverage. We'll move on to next slide. Problems in wireless networks. Wireless networks face unique challenges such as hidden and exposed nodes problem, signal fading, bandwidth limitations, power constraints, and ensuring quality of service. Techniques like rate adaptation and power control help address these issues. In this slide, we discuss about the wireless network security. Security is a paramount in wireless networks because the broadcast nature of radio transmissions makes interception relatively easy. Authentication verifies the identity of the devices attempting to connect to the network. There are several authentication matrices. Open authentication performs no actual verification and it's inherently insecure. Shared key authentication uses pre-shared keys, but it is vulnerable to eavesdropping. IEEE 802.1x/EAP frameworks provide robust enterprise authentication, supporting methods like digital certificates, token cards, and secure password protocols. Encryption. Encryption protects the confidentiality of transmitted data. Methods include WEP method, wired equivalent privacy, WPA, Wi-Fi protected access, WPA2, advanced encryption standard algorithm, WPA3, introduced in 2018, further strengthens security is improved, key establishment, and protection against offline dictionary attacks. Access control determines which authenticated device can access network resources. MAC address filtering restricts access based on the device hardware addresses. Through this can circumvented by MAC spoofing. Remote authentication dial-in user service provide centralized authentication, authorization, and accounting for enterprise networks. We'll move on to next slide. Wide area networks. Wide area networks extends over large geographical areas, connecting local networks across cities, countries, or globally. WAN technologies encompass various approaches to long-distance connectivity. Lease lines, dedicated point-to-point connections with guaranteed bandwidth but at high cost. Circuit switching establishes a dedicated path for duration communication as in traditional telephone networks. Packet switching divides into packets that are routed independently, sharing network resources more efficiently. Cell switching uses fixed size cells for transport as ATM asynchronous mode. Frame relay, variable size frames with minimal error checking, can be transmitted via wide area network. We'll move on to next slide. TCP/IP operation in the wide area network. The TCP/IP protocol suite enables end-to-end communication across diverse networks, including wide area networks. Addressing and routing facilitate global connectivity. IP addressing provides globally unique identification for devices. Hierarchical routing enables scalability across large networks. BGP, Border Gateway Protocol, handles routing between autonomous systems that make up the internet. When it comes to performance consideration in wide area network, longer propagation delays affecting TCP performance as acknowledgement take longer to return. Bandwidth delay product impacts optimal window sizes. A high bandwidth, high latency connection requires larger windows. Path MTU discovery present fragmentation that would reduce efficiency. And when it comes to quality of service in wide area networks, mechanisms quality of service mechanisms prioritize traffic based on requirements. Differentiated services classifies and manages traffic by type. Integrated services reserves resources for specific traffic flows. Resource reservation protocol handles signaling for resource reservations. Let's move on to next slide. TCP/IP in LAN and WAN. TCP/IP differs significantly between local area network and wide area network environments. In local area network, latency is typically low. It can be microseconds to milliseconds. Bandwidth is high and consistent. Congestion is less frequent, and packet loss primarily occurs due to collisions. TCP optimization focuses on collisions avoidance and efficient local delivery. In wide area networks, latency is much higher, milliseconds to seconds. Bandwidth may be variable and constrained. Congestion is common, and packet loss occurs due to congestion and buffer overflows. Error rates are generally higher, especially in wireless wide area networks. TCP requires larger window sizes for efficiency, and optimization focus on congestion control bandwidth utilization. We'll move on to next slide. In this slide, we'll discuss about the client-server model. The client-server model structures distributed applications with distinct roles. Characteristics include asymmetrical relationship where servers provide resources and client consume them, typically in one-to-many pattern. Communication flow is a request-response pattern where clients initiate interactions. Server types include file servers managing shared storage, web servers delivering hypertext protocol, content database servers handling data storage and retrieval, and application servers executing business logics. This model provides centralized resource management, scalability, and separation of concerns, but can create bottlenecks and single point of failures if not properly designed. In this slide, we'll discuss about the connection-oriented communication. In connection-oriented communication involves a dedicated path for data exchange. It has a three-phase process, ensures reliability and manage flow control. Examples include transmission control protocol and stream control transmission protocol and virtual circuits. When it comes to advantages, guaranteed delivery and ordered data transfers, while disadvantages include higher overhead and increased latency. We'll move on to next slide. Connectionless communication. Connectionless communication transmits data without prior connection. It has no connection pace, treats each packet independently, and lacks of reliability guarantees. Examples: user datagram protocol, internet protocol, and internet control message protocols. Advantages in connectionless communications: lower overhead and latency, efficient for occasional or small data transfers. Disadvantages include no guaranteed delivery, ordering, or flow control. We'll move on to next slide. In this layer, we'll discuss about the logical link control layer, LLC. The logical link control layer serves as the upper sublayer of the data link layer in the OSI model. Functions include multiplexing, demultiplexing using service access points, flow control through sliding window protocols, error control via ARQ mechanisms, and connection management for connection-oriented services. Types of logical link controls are: type 1 is connectionless acknowledged services, type 2 is connection-oriented acknowledged services, and type 3 is connectionless acknowledged services, providing flexibility for different application requirement. We'll move on to next slide. In this slide, we'll discuss about the data sent through a wide area network. Data traversing a wide area network undergoes multiple transformations, such as application layer is generated and formatted, transport layer adds segmentation, flow control, and error recovery. Network layer provides the routing information for global addressing, and the data link layer applies wide area network specific encapsulations, example PPP and frame relays. Physical layer converts to appropriate signals for transmission. The specific encapsulation depends on wide area network technology in use. Frame relay uses frames with DLCI identifiers. ATM segments data into 53-byte cells. MPLS adds labels, stacks, and lease line typically use HDLC or PPP framing. We'll next move on to next slide. In this slide, we'll discuss about the data link layer operation of a wide area network. The data link layer in wide area network ensures reliable connection through framing, addressing, error detection, flow control, and access control. Different wide area network technologies like point-to-point protocols, frame relays, ATM, and multi-protocol label switching implement these functions uniquely. We'll move on to next slide. How to send a message to a group of computers. To send messages to multiple computers, you can use broadcast, multicast, anycast, or application level group communication. Each method has its own advantages and limitations, especially in wireless environments where multicast and broadcast require careful handling. When it comes to conclusion of this presentation has covered essential knowledge for understanding wireless communication systems. Key insights include layered architecture, physical constraints, multiple access technologies, security concerns, and convergence with wide area networks. As wireless network technologies involve, mastering these concepts is crucial for future innovations. Thank you.